Look at this arrow. That's a vector. Now check this out. Just two numbers in brackets. Also a vector. And this weird abstract thing, yup, also a vector. Here's the rule. A vector is anything you can add and scale. That's it. That one idea runs all of linear algebra. It runs your video games, your photos, the AI finishing your sentences right now. Same idea, 3 costume. Quick question, which one did your teacher start with? The arrow, the list, or the abstraction? Comments below. In the next 8 minutes, all 3 definitions collapse into one. Right here on screen, no prerequisites. Seriously, if you can add numbers, you can do this. This is what a vector really is. Part 1 of linear algebra for beginners. Look at this arrow on screen. Physics says that's a vector. It's got a length and it points somewhere. Simple. You see this all the time. A force pushes a box. Wind pushes a sail. The arrow tells you how hard and which way. For physics, this definition is perfect. But computing disagrees. To a computer, a vector's just a list. 2 numbers in a strict order. That's it. Great for code. Now the third definition, the abstract one, sounds completely useless, and yet it's what powers the AI on your phone. Hold that thought. Mathematics says a vector is an element of a vector space defined only by the rules it obeys. No picture, no numbers, just rules, deliberately abstract. 3 definitions, 1 object. They can't all be the whole story, and yet somehow they're all true at once. Here's how. We'll build the answer in 5 steps. Arrows first, then numbers, then the 2 moves that define everything, then the payoff. Stay with me. Step 1 is done. You've met the 3 rivals. Now step 2, we put an arrow on a graph and watch it turn into numbers. Draw a flat plane, 2 axes. Every vector you'll ever need starts right here at the origin. Watch. Walk 3 units, right? You can see it on screen. Then 2 units up. Draw the arrow from where you started to where you stopped. That's the physicist's vector. We'll call it V. Now drop a line from the tip straight down to each axis, 3 units along X, 2 along Y. Those shadows are the vector's components. Remember them. And here's the most important 16 seconds of this video. Don't blink. Watch the arrow fold down onto its own shadows. Here's the takeaway, the arrow and the number pair. Same object, 2 faces. A computer can't picture an arrow, but it can picture 3, 2 just fine. Geometry becomes numbers. Numbers become geometry. This dictionary runs the rest of the course. Step 3. What does it mean to add 2 vectors? Meet W1 unit, right. 3 units down. A perfectly good vector with its own components. Watch what happens next. To add W to V, pick W up and place its tail on the tip of V like you see on screen. Now walk 3, right. 2 up, then 1 right, 3 down. Where you land is the sum, 4 right, 1 down, a brand new vector, V plus W. Now, forget the arrows for a second. Look at the numbers on screen. Pure arithmetic. 3 plus 1 is 4. 2 minus 3 is minus 1. Same answer, twice. Geometry and arithmetic agree, always. That's not luck, it's the design. And here's the thing. Order doesn't matter. Watch. Walk W first, then V. Different path, same destination. 4 minus 1 every single time. Addition of vectors is commutative. So, vector addition is just walking. And walking is just adding components. 2 pictures, 1 operation. Next, the second move stretching. It completes the game. Step 4. Multiplying a vector by a plane number, a scalar. 2 times V watch, same direction. Twice the walk, 6 right, 4 up. Every component doubles, 3 becomes 6, 2 becomes 4. Half of V shrinks it, 1.5, 1. And a negative scalar, look at this. Minus, V flips you around. 3 left, 2 down. Opposite direction, same length. And 0 times V, watch. The arrow collapses to a dot, the 0 vector. No walk, no direction. It's the only vector that points nowhere, and trust me, it matters more than it looks. See the pattern? Scaling a vector scales every component. No exceptions, that's the whole rule. So now you own both moves. Add tip to tail, scale component by component, 2 moves. That's the entire game. Let's take stock. You've seen both moves on screen now, adding tip to tail, scaling component by component. And here's the kicker. Every big idea in linear algebra matrices, determinants, eigenvalues, is built from just these two moves, nothing else. But if that's all a vector is, then anything you can add and scale counts as a vector. Look at the arrows on screen. They're just one example. Anything qualifies. Arrows, yes. Number lists, yes. But keep going. What else obeys those two rules? Pause the video. Comment one thing you think qualifies before I show you mine. Ready? Watch this. This is where it clicks. Step 5. This is the payoff. You've been patient, and here's where it all comes together. Look at this curve on screen. F of x equals x squared. A function, not an arrow, not a list. Remember it. Here's a second function, sine of x. Now watch closely. We can add them, point by point, height by height. A new curve is born, f plus g. Remember the rule, you've heard it before. Add it and scale it. It's a vector, functions qualify. Look at these three sample points. At each one, the green height is the gold height plus the blue height, addition but of functions. And we can scale. 2 times f stretches the whole curve vertically. Watch every value doubles. So functions pass both tests. Add them, scale them, they behave exactly like vectors. And here's where it gets wild. A polynomial, 1 plus 2x plus 3x squared, that's just the list 1, 2, 3 dressed differently. I know. It feels abstract, but it's not useless. The next 90 seconds will change your mind. Field trip. 1. Every pixel on your screen is a vector. 240 parts red, 160 green, 48 blue. Mixing colors is vector addition. This gold you're looking at, one vector plus another. 2. Every game engine. Your character's velocity is a vector. Gravity is another. 60 times per second, the engine adds them and scales them. The exact 2 moves you just learned. 3. Artificial intelligence. Words are stored as vectors, and here's the famous result that blew everyone's mind. King minus man plus woman gives queen. The AI isn't reading. It's doing vector arithmetic on meaning itself. Arrows, lists, functions, colors, words. Look at all of these on screen. One idea. So what can you build with it? Back to the plane. You see v and w on screen side by side. One last experiment. Take every possible multiple of v, every possible multiple of w, add each pair. What shape do the results make? Watch the destinations light up on screen. They cover the entire plane, every point reachable, every single one. We call this set the span of v and w. Their span is the whole plane. But here's where people mess up. If w pointed exactly along v's line, every combination would collapse onto that line. Span can shrink. When it does, some destinations become unreachable. Span decides whether your equations have solutions at all, and that's exactly what we'll explore in episode 2.